In our last video cast, Chapter 3, we'll look at limiting reactants, and we'll also look at theoretical and actual yields that lead us to calculate the percentage yield of a reaction process. Let's pretend that you're in the business of manufacturing cars, and let's just say that to manufacture a car you need one car body per car, and then you also need 4 wheels to make that car. In this manufacture of cars, it could be kind of like a chemical reaction where you'd say one car is produced using one body, 4 wheels to make one car. In this chemical reaction, or in this make-believe reaction where we make cars, let's say that your company happened to have 10 car bodies and it also happened to have 10 wheels. If we look at this closely and we'd say make as many cars as you can, all of a sudden you'd have one of the 2 reactants that limited your production of cars. As a matter of fact, if I look at it, I could only make 2 complete cars from this, and I'd end up, well, at the most, making 2.5 cars before I ran out of wheels, because I need 4 wheels for every car. Now, if I had an unlimited amount of wheels, I could make 10 total cars, because my limiting reactant then would be the bodies of the cars. And this is the type of idea that we're going to learn today in limiting reactants in stoichiometric chemistry. Every reaction is kind of like putting together a car or putting together some type of chemicals. The 2 or 3 or 4 or 5 chemicals that come together each have to be in particular amounts to be either completely used up or to be what's called the limiting reactant, or limit the amount that we have to produce however many of the products that we're going to make. Limiting reactants are also sometimes called limiting reagents. A reagent is a chemical that's a reactant on the left side of the chemical reaction. And the limiting one, of course, is the one that is available in the smallest amount, using the coefficients of the balanced chemical equation to determine which one it is. I'll show you a quick and easy way to determine which one's the limiting reactant for various chemical reactions. Let's take a look at this sample problem. It says, how many moles of NH3 can be formed when 3 moles of N2 and 6 moles of H2 are put together in a beaker or in a flask? Note, in this example, we'll use what's called an ICE table. The balanced chemical equation is 3H2 plus N2 goes to 2NH3. And I'm just going to rewrite this a little bit larger so you can see it on a little bit bigger scale. 3H2 plus N2, and notice I'm going to space it out quite a bit, goes to 2NH3. And after I do this, I'm going to write a little table down below this. I'm going to write I for initial, C for change, and then lastly E for end, and how much I'll end up with at the end of the reaction. Some people call this an ICE table because I-C-E spells ice. And then in this table what I'll do is I'll put my amounts of hydrogen, my amounts of nitrogen, and then eventually my amounts of NH3 or ammonia that are produced. So looking back at my question, it tells me that there are 3 moles of nitrogen and there are 6 moles of hydrogen. So 3 moles of nitrogen is how much I initially have. 3 moles of nitrogen. 6 moles of hydrogen is how much I initially have. And it doesn't tell me anything about the ammonia, the NH3, so I'm going to assume that I start with 0 of that. Now, looking at the balanced chemical equation and relating it kind of to the cars thing that we did up above, which one of these 2 things is going to run out before the other one? Now, if you're not sure, here's the quick and easy dirty way to do it. Take the number that you have and divide it by its coefficient. Take the number that you have and divide it by its coefficient. Once you've done the division, 6 divided by 3 would be 2, 3 divided by 1 would be 3. Whichever number is smaller is the limiting reactant. Whichever number is smaller is the limiting reactant. And so we'd say, therefore, hydrogen limits the production of the ammonia because it's present in the smaller amount with a 3-to-1 ratio. Now, another way to do this, and the way some other teachers teach it, is to say, compare hydrogen to ammonia and compare nitrogen to ammonia in separate equations. And if you do that, you can say, okay, I have 6 hydrogens, and for every 3 hydrogens, I will produce 2 ammonias. And 6 times 2 is 12 divided by 3 is 4, so I'd produce 4 ammonias this way. And the other way I could say is I have 3 nitrogens, and now compare it to ammonia, and for every 1 nitrogen, that's the 1 right here, I'm going to make 2 ammonias, 2 NH3s. 3 times 2 is 6 divided by 1, I'd produce 6. Now look at whichever one would produce the smallest amount of the product is my limiting reagent. So if you like doing the comparison like this, of putting the stoichiometric ratio in and figuring out which one of the reactants is going to end up giving you the smallest amount of product, that's fine. If you like the simple, quick, and dirty way of just divide it by its coefficient and see which one's the smallest, that's okay too. That's okay too. It's the same method, actually, if you look at it kind of closely, because you'll notice both of them are multiplying by 2, which is the amount of product that you're going to get, and each one is just simply dividing by its coefficient. Simply dividing by its coefficient. If there's more than one product produced, you can still do this. Just make sure that you're comparing both of them to the same product in the end. I still think that the easiest way is to just take your amount of moles of each and then just simply divide it by the coefficient and find out which one's the smallest, and then you know what the limiter is. Once you know which one limits, ignore the division that you did before and just know that this one is going to get used up, and say, in my change I'll use up all of the limiting reactant. I'll lose 6 and I'll end up with 0. Since it's the limiting reactant, I'm going to use up all of it that I have, and I'll end up with a 0 amount here. Now, to figure out how much nitrogen I'm going to use up, I need to do a comparison between nitrogen and the limiting reactant. The limiting reactant, of course, we figured out was hydrogen. So to do this, I need to take and ask the question, how much nitrogen will react with my 6 moles of hydrogen? So start with the 6 hydrogen, and write a little relationship between hydrogen and nitrogen. Notice I'll put N2 as my new set of units, hydrogen as my set of units that I have right now, and I will have a 3 in front of the hydrogen and a 1 in front of the nitrogen, because these are the coefficients in front of the balanced, in front of the reactants. 6 times 1 divided by 3 ends up equaling 2, which means I will lose 2 nitrogens when I react with all of my hydrogen. Now, for some people that can be real obvious to say, for every 6 of these, I'll lose only 2 of these, because my ratio is 3-to-1. I'll lose 3 times as much of this stuff as I will this. And of course, 3 times 2 is 6. So if you can do it in your head, that's okay too. But if you need to, you can do the math right here and just take the amount of hydrogen that you have, or take the amount of the limiting reagent you have, and multiply it by a ratio, a stoichiometric ratio from the balanced chemical equation, putting the thing that you want to know on the top and the thing that you already know in a position where it's going to cancel. So I'll lose 2. So 3 minus 2 is 1. So I'll end up with 1 mole of the N2 remaining, 0 moles of the hydrogen, and then I'll take my limiting reagent once again and I'll compare it to my product. Compare it to my product. And I know I'm losing 6 moles of hydrogen, 6 moles of hydrogen, and I have to ask the question, how much NH3 will be produced? How much NH3 will be produced? And put my hydrogen in a position where it's going to be canceled. and compare it. For every 2 ammonia that's produced, 3 hydrogens are lost. So 6 times 2 is 12, divided by 3 is 4, which means I will gain 4 moles of NH3. 6 times 2 is 12, divided by 3 is 4. So I'll end up with 4 moles of NH3 that will be produced. So doing it with an ice table like this, an initial, change, and end table, allows me to calculate not only how much of the product will be produced, it tells me which one's my limiting reagent will be used up, and it also tells me how much of the excess reagent or reagents will be left over. There'll be 1 mole of this sitting in the beaker not used up at all. Let's go on and let's do a second example problem. This one just asked about how many moles of NH3 would be formed, but many times they ask you, as we had in other stoichiometry problems in the last video cast, not how many moles are left over, how many moles are produced, but how many grams are left over, how many grams are produced. So turn to the next page and let's consider this reaction. It says that 2 aluminums plus 3 chlorines make 2 AlCl3, and it says a mixture of 54 grams of aluminum and 142 grams of chlorine are allowed to react in an enclosed vessel. First of all, determine which is the limiting reactant. Second, how many moles of AlCl3 are formed, and then lastly, how many moles of excess reactant remain at the end of the reaction. Now you can follow your same steps that you learned when you did stoichiometry problems before. Step number 1 is to write the balanced chemical equation, which is already done for you. I'm just going to write it a little bit bigger so I can write a table below it. Step number 2, of course, is to convert to moles. So I'll put my initial, change, and end table down here. ICE, remember I stands for initial, C stands for change, E stands for end, and I'll always lose stuff on the left side, gain stuff on the right side, just as you'd imagine in a chemical reaction. So step number 2 is to convert to moles, and then of course step number 3 is to use the mole to mole ratio in the balanced chemical equation. But before we can do that, we have to figure out which one is the limiter. And remember, there's a couple of ways you can do that, and I'll go through one way as we do this. So step number 2 now, convert to moles. I'm told that there are 54 grams of aluminum, so 54 grams of aluminum. And if I look on the periodic table, aluminum has an atomic mass pretty close to 27, 26.98. So I'm going to use 27. Put grams of aluminum in a position where it's going to cancel. Moles is my new set of units, and in 1 mole there's 27 grams. 54 divided by 27, lo and behold, you don't even need your calculator, turns out to be 2 moles. So I start with 2 moles of aluminum. Now I need to calculate how much chlorine I have. And in this case I'm told I have 142 grams of chlorine. Put a multiply sign, put a line, put grams of chlorine in a position where it's going to cancel, and put moles as my new set of units. And if you look on the periodic table, chlorine has an atomic mass of about 35.5. So it's going to end up for Cl2 being about 71 or so, 35.5 times 2. So there's 71 grams in 1 mole. And hey, 142 divided by 71, once again, I don't need my calculator, turns out to be about 2 moles of chlorine that I initially start with. I should probably move this C down just a little bit. I'll move my E down the table a little bit so I have a little more room. So I start with 2 moles here, start with 2 moles here. It doesn't tell me anything about AlCl3, so I'm assuming I'm going to start with 0. So that's step number 1, write the balanced chemical equation, and step number 2, convert to moles. Now, before you can do step number 3 and use the mole to mole ratio, you need to figure out which one the limiting reagent or limiting reactant is. And to do that, remember, the quick and dirty way is to take your number of moles and divide it by the coefficient. Divide it by the coefficient. And then ask which one would end up being smaller. And many times you don't even need to do the calculation on your calculator. You just need to recognize that one of them is going to end up being smaller when divided by its coefficient than the other one. In this case, 2 divided by 2 would be 1, and this would be 2/3, and of course 2/3 is smaller than 1. So I know that the chlorine is going to end up being my limiting reactant because it's the smallest, which answers letter A up here, which is the limiting reactant. Which, when I fill in my ice table now to help answer B and C, I know I'm going to use up all of the chlorine I have. So I have 2 moles, I'll use up 2 moles, and I'll end up with 0 0 moles right here in the end. So doing my ice table, start with 2, lose 2, end with 0. I could immediately go and relate my chlorine, my limiting reactant, to the AlCl3 over here. And I can say if I lose 2 moles here, that means I'm going to gain 2 moles of the chlorine and compare it immediately to AlCl3. Okay, AlCl3 is my new set of units, Cl2 is my old set of units, and if I look up at the balanced chemical equation, there's a 2 in front of the AlCl3, there's a 3 in front of the chlorine, so 2 times 2 is 4, divided by 3 is 4/3, so I'll gain 4/3, which is what, 1 1/3 or so moles of AlCl3, and in the end, at the bottom of my ice table down here, I'll end up with 1.333 repeating moles of AlCl3, which answers question B, how many moles of AlCl3 are formed, and that's 1.33 moles. Notice I used the limiting reactant and then used the stoichiometry based on a 3:2 relationship right here, relating those two. The last question, letter C, says how many moles of excess reactant remain, and I know that I'm going to have excess aluminum here, but what I want to find out is how much aluminum is actually going to be reacted with. So start with your amount of chlorine, and I'm told I have 2 moles of chlorine. I'm going to lose 2 moles of chlorine, and write that down, 2 moles of chlorine, and then relate it to the aluminum. Relate it to the aluminum. So put aluminum as my new set of units, chlorine as my units in a position where it's going to cancel, and their relationship is 2 to 3. For every 2 aluminums, there's 3 chlorines. 2 times 2 is 4, divided by 3 is 4/3, or 1 1/3 or so, and that's how much I'll lose of my aluminum. Notice the chlorines canceled, and that's how much aluminum I lose. Now doing my subtraction, 2 minus 1 1/3 ends up being approximately let's see, in decimals, I think that'd be like 0.6667 or so moles that I'd have remaining in my of my aluminum in my excess reactant. So for A, B, and C, which is the limiter, chlorine ended up being the limiter. How many moles of AlCl3 formed? 1.33. And how much of the excess reactant remained? 0.66 moles. Let's look at one more sample problem using limiting reactants. Now, if you feel pretty good about these limiters, feel free to go ahead and skip over this part of the video. But if you'd like to see a second limiting reactant example, here's another one where there's a little more converting to do, and we use all 4 steps of stoichiometry, including the intermediate step between 2 and 3 where you have to determine what the limiter is. This one says a 55-gram sample of pure iron is submerged in a solution containing 338 grams of silver nitrate. Iron nitrate and solid silver are the products. So, step number 1, write the balanced chemical equation. So, iron is submerged into a solution containing silver nitrate, AgNO3, and it tells us that one of the products that is formed is solid silver, and the other product that's formed is FeNO3. To balance this chemical equation, I'd need a 3 right here, which forces me to put a 3 in front of the silver. And I think I have 3 nitrates now, 3 nitrates, 3 silvers, 3 silvers, and that's my balanced chemical equation. Step number 1, write the balanced chemical equation. Step number 2 now, it asks determine what the limiting reactant is, so I'm going to write an ice table over here, I, C, E, and try to get that onto the screen here. I can get the I on there anyway. And before I can determine what the limiter is, I need to know the number of moles of the 2 reactants that I have. And it tells me that there are 55.8 grams of iron. Put grams in a position where it's going to cancel. Moles is my new set of units. And if I look on the periodic table, it turns out that iron has an atomic mass of 55.85. Ooh, who wrote these problems? The math is going to work out really nice. 55.8 grams in 1 mole. So 55 divided by 55 turns out there's 1 mole of iron to start with. Pretty good. And then AgNO3, there are 338 grams of the silver nitrate. and we're going to have to convert that to moles. So put grams in a position where it's going to cancel. Moles is your new set of units. And silver, if you look on the periodic table, is 107. Let's see, where's silver? Right there. Almost 108. And then nitrogen is 14, and oxygen, of course, is 16. And so I've got 1 silver, 1 nitrogen, and 1 oxygen. So 108 plus 14 plus 16, 3 of them. And that turns out to be 170 or so. And 338 divided by 170 is going to be close, pretty darn close to 2. So I'm just going to approximate and round just a little bit. And I'm going to say that I have 2 moles of silver nitrate to start with. So 1 mole here, 2 moles here, and now I can determine the limiter. Remember, the quick and dirty way to find the limiter is to take your number and divide it by the coefficient. Take your number of moles, divide it by the coefficient. Now, a novice chemist would look at this right away and say, well, I have twice as much of the silver nitrate, so for sure this one's going to be in excess. But you can't know until you look at the coefficients. This one would be divided by 1. This one would be divided by 3. Who's going to end up being the smaller number? Well, obviously 2/3 is smaller than 1. So this guy is going to limit the reaction. Now, don't fall into the trap of taking 2 divided by 3 and then using that as your number of moles. Remember, the only reason that you're dividing by the coefficient is to determine the limiter. Then go back and use the number of moles you have to work the rest of the problem. So that answers letter B, determine the limiting reactant. Then letter C, it says determine the moles of each product produced. So if this is the limiter, I know I'm going to have a change of -2, and I'll end up with a 0 of this guy. Okay? And then I need to figure out how much iron I'm going to lose. And I know I'm going to lose 2 moles of the AgNO3. Put a multiply sign, put a line, and put my AgNO3 in a position where it's going to cancel, and put my iron as my new set of units. And for every 1 iron, which I get from right here, there are 3 silver nitrates used up. So 2 times 1 divided by 3 is 2/3. So I'll lose 2/3 right here, and 1 minus 2/3. 1 mole minus 2/3. The amount of iron that I'll lose is 1/3, or I'll write it in decimals, 0.333 moles. Okay, so this is my number of moles of iron that I will have remaining. I'll have 0 remaining of my silver nitrate. And now I can do my comparison here between my limiter and my products that are formed over here. I'm going to lose 2 moles of AgNO3. How much silver would be produced? And this one's actually pretty easy. You can do it in your head, because for every 3 of these I lose, I'll gain 3 of these. So if I lose 2, I will gain 2 over here. Yes, 2 moles of silver. Oh, I forgot to put up here initially. I'll have 0 of both of those. So I'll gain 2 right here, and so in the end I end up with 2 moles of the silver. And then lastly, it's a 3-to-1 ratio between silver nitrate and iron nitrate. So I'll lose 2 moles here. So I can put lose 2 moles of the AgNO3. And then what I want to know is how much FeNO3 will be produced, and put AgNO3 in a position where it's going to cancel, and look at my stoichiometry. There's a 3 here and a 1 in front of this one. So for every 3 silver nitrates that I lose, 1 iron nitrate will be produced. So 2 times 1 divided by 3 means I'll gain 2/3 of a mole right here. And if I put that into decimals, I believe I'll end up with 0.667 or so moles of the iron nitrate. Now, the question actually didn't ask for the moles. It asked for the mass of the each product produced, and it asked for the mass of the excess reactant remaining. So we have to go to the 4th step of stoichiometry, which is after we've done the mole to mole ratios, convert to the asked for units. And the units they ask for are grams. So we need to take our iron and convert it to grams, 0.333 grams of iron, and there are approximately 56 grams in 1 mole. I've got 2 moles of silver that are produced, and there's about 108 grams in 1 mole here. And lastly, there's 0.667 moles of the iron nitrate. Oops, there's a 3 there, and let's see, I got to add that one up. I'm not sure what that one is. Iron is 56 plus 14, 3 of those, plus let's see, 3 times, whoops, there's a 3 here and a 3 here, so 9 times 16, I get 242. I hope my math is right there. 667 moles, my arithmetic. So there's 242 grams in 1 mole there. So 0.667 times 242 turns out to be 161 grams of iron nitrate that's produced. 2 times 108, that's 216 grams of the silver that would be produced. And 0.333 times 56 turns out to be about 18.6 grams of iron that's produced, which answers all of my questions. Determine how much of each of the products is produced and how much of the excess, the reactant, is left over. Long problem? Yeah, that filled an entire page. Holy cow. Lastly, in this video cast, we're going to talk about theoretical and actual yields. A theoretical yield is a quantity of product that is calculated to form when all of the limiting reactant reacts. The amount of product actually obtained in a reaction is called the actual yield. And using both of those, we can find something called the percentage yield. And percent is equal to actual amount that we get divided by the mathematically calculated theoretical yield times 100%. Actual divided by theoretical times 100%. In the last problem, 2 moles of silver were theoretically produced. Calculate the mass of silver that would theoretically be produced. Oh, I guess we did that in the last problem. We figured out down here that the mass of silver was 216 grams that would be produced. So in letter A, 216 grams of silver was produced. And then in letter B it says, if 107.8 grams of silver were actually produced, calculate the percentage yield. So to find percentage yield, we take actual, 107.8, and divide it by the theoretical, which was 216 grams, and then we multiply that by 100%, and I think I can approximate this to be about 108. So 108 divided by 16 is like 0.5 or so, times 100% means I'm going to end up with about a 50% yield, pretty close to a 50% yield. So notice it's actual divided by the theoretical, and the theoretical I get by doing the stoichiometry, times 100%. In a second new chemical reaction, the actual yield of silver was 75%. Now, how many grams of silver were actually produced? Okay, so this is using the same equation where we say percent yield is equal to actual divided by theoretical. And we're told that the actual, times 100%. I'm sorry, I forgot to put that in there. The percent yield was 75%, so I'll put that in here. 75 is equal to the actual, that's the thing that I want to find, divided by the theoretical. And if I look back up here, my theoretical yield was 216 grams. I did that by doing the stoichiometry in the last problem. So 216 grams goes down here, times 100%. 100%. Now this 1% right here doesn't mean right in 0.1 or 1.00 or something like that. It's like a set of units. So divide both sides by 100. So I end up with 0.75 is equal to my actual divided by 216. Multiply both sides by 216. And 216 times 70, or 0.75 is 162. So my actual yield would be 162 grams. That is theoretical and actual yield. And just remember this equation, because many times they'll give you the percentage yield, or you'll have to calculate it just like we did in this problem right here. Good luck with your limiting reactant stoichiometry, your theoretical, and your actual yields.